Well, hello everyone. Mrs. Hanson once again, continuing our lessons with our chapter 4, alkanes and cycloalkanes. This section we start to look at our alkenes in three-dimensional kind of an opportunity to start twisting these sigma bonds and taking a look at the most stable arrangement of kind of putting all of the substituent groups in alleviating any kind of steric hindrance or high energy conformations. So that's the idea behind a Newman projection. Let's notice that there are several different ways we can represent the three-dimensional shape of a compound, and I must say that a molecular model kit will go a long way in this section. I can't encourage you enough to get your model kit out and start staring down single bonds as you twist and rotate these sigma bonds. You get a much better feel for what's happening when I try to draw a picture. I know that a picture is very valid, but a model kit, way better. So kind of consider building these and staring down these single bonds from one carbon to the next as you practice drawing Newman projections. We know that single bonds rotate, and it results in a multiple, an incredible wide variety of shapes called conformations. When I think of conformations, think of all the possible three-dimensional shapes based on simply rotating a carbon-to-carbon single bond. One way that we've been practicing representing three-dimensional shapes on a flat piece of paper is a wedge and a dash. I know that if I see a wedge, I know that it's coming out of the paper, and I know if I see a dash, it's going behind the paper. And if it's in the same plane as the paper, you see a solid line, a dash-wedge system, which is great. A sawhorse will take the two carbons, and it's called a sawhorse simply because you see two legs coming down on each one of those carbons. You see a head and then the tail. So it has more of a sawhorse, kind of just think of it like this, and that tail and head coming out like that. And then a Newman projection, and these are maybe perhaps brand new for you. Newman projections are ideal for comparing relative stability of possible conformations resulting from single bond rotation. When we look at drawing a Newman projection, that represents a carbon, what I just highlighted. This carbon, if I just think about the compound I'm drawing, CH3, CH3, there's a two-carbon structure, and each of those carbons is bonded to three hydrogens. The first carbon is represented by a single line, and all three of those bonds then are shown leading to hydrogen. What you then have to envision is going from carbon 1 back to carbon 2. This open-ended circle is behind carbon 1. Remember that if you're looking from carbon 1 to carbon 2 and your eye is looking right here, kind of think of that as your viewpoint. Well, that's a backward eye, Linda. So kind of think of that this would be your eye and you're looking down this bond. So the carbon represented in carbon 2 is behind carbon 1. So to see it, I've got to make it bigger. Carbon 1 and behind it carbon 2. And there's its three hydrogens in a Newman projection. It's going to take some practice, and I encourage you to get your model kits out. This Newman projection is the perspective of looking straight down a particular sigma bond between two carbons. We show the front carbon as a point and the back carbon as a large open circle behind it. Here are those two carbons I represented on the previous page, carbon 1, carbon 2. So this is just simply an ethane molecule, CH3, CH3. Carbon 1 is represented as a point. It's attached to three hydrogens. That's this front carbon. And when I model what I see coming from it, I notice that I have three hydrogens coming off of C1. Looking straight down that plane, carbon 2 is hidden behind carbon 1. You don't see it because it's hidden directly behind. So we have to draw it as an open circle so you can literally see it behind. So this represents carbon 2, and this point is carbon 1. And we can see these 60-degree bond angles between the front and the back hydrogens. The hydrogens that are on the front carbon are highlighted in red, Those hydrogens that are highlighted in blue are on the back carbon, carbon 2. Build this and prove it to yourself that the model looks just like this, staring down one black ball atom of carbon to the next black mottled ball of carbon. And remember, this bond is just completely free to rotate. And so you can hold one atom still, let's just say hold the front carbon still, and spin the back carbon. And what do you see? You see all the possible conformations of ethane. If I have a hydrogen, and I'm just going to leave the front one fixed, and I have the back carbon, one way I could spin this is so that the two hydrogens, I mean, think about it, if I take this hydrogen and spin it 60 degrees, it's now going, whoops, I shouldn't start there. It's now going to come off and be directly behind the front hydrogens. So all hydrogens could be hidden from the front carbon to the back carbon, or I can give them a whole lot of space and put about 60 degrees between those. On the front carbon, these are about 120, but between the front hydrogen and one from the back, it's about halfway, so you can see it's about 60. When you build these, and please do so, and stare down one carbon bond to the next, you're getting an idea of the term conformations, all the different twists of a single bond and what happens to the attachments in relationship to the other bonded atoms. So you need a perspective to draw a Newman projection. So for instance, if this were a homework question that's telling us you're the observer, let me put a screen up and kind of talk through this slowly. You are the observer. That's your eye in a 1, 2, 3, 4 carbon chain. So this would be 2, 3 dibromobutane. You're told to look between carbon 2 and carbon 3. So when I make a point and I draw what I see, I am drawing the perspective from carbon 2. So just keep in mind, when you drew the point, that represents carbon 2. That's this guy right here. What do you see? Coming straight down from the carbon, I see a methyl group, a CH3. Notice that this bromine here is a wedge, so that's coming out and to the right, but I'm only going to draw it as a solid line. We're not using dashes and wedges in a Newman projection, but it's coming out and to the right. And what's not shown, but you know is there, is a dashed line letting you know that hydrogen was behind that carbon, that bromine, so you can see the 4 bonds. This carbon, called C2, leads to a methyl group down, leads to a bromo group up and to the right, and a hydrogen up and to the left. And that's what we drew with that particular structure. Now turn your attention to the 3rd carbon, C3. I'll change color to red. What do we see? Well, first of all, notice that we use an open circle to represent the carbon 3. That's because when I'm looking straight down the bond from carbon 2 to carbon 3, I don't see that 3rd carbon. It's hidden directly behind carbon 2. And so therefore I use a large circle to let you know it's behind carbon 2. What do we see? From carbon 3 coming up, I see a hydrogen. So notice I'm going to put an H right up front. Coming down and to the right, you see a bromine. And so I'm going to say a bromine here. And then coming as a dash would be that hydrogen in the other direction. So that's the skill as you're learning to go step by step. What do we see and how is it coming out of the paper? Notice at carbon 2, we had a methyl group. The methyl group was pointing straight down. So we took that carbon 2 as a dot in the center and drew a methyl straight down. Coming up and pointing to the right was a bromine. That was denoted this direction. And then we had to assume that the hydrogen was a dash and we put it up and to the left. So the first carbon, methyl group down, you might see that abbreviated Me for methyl, the bromine, and the hydrogen. Then you examined carbon number 3 in that fourth carbon, that 4-carbon chain. Here's C3. Notice that we make that an open circle. We saw a methyl group, we saw bromine coming out of the page, and we saw a hydrogen going behind the page. So we took care of carbon 3 with an open circle. And then finally, we just added those two pieces together. This represents the attachments of carbon 2. The open circle represents all the attachments of carbon 3. Carbon 3 had a bromine, a hydrogen, and a methyl. That's the skill of drawing a Newman projection. It really takes a little bit of practice with your model kits to get a good image of what I'm trying to draw on a flat piece of paper. Don't short yourself the opportunity to build these models and examine them for yourself in 3 dimensions. Can you look at this compound and envision it from a Newman projection? That's your challenge in this section, and that's what I'm encouraging you to build the models and convince yourself how to draw them on a flat piece of paper. Draw a 3-dimensional object. So notice here we have a 1, 2, 3 carbon chain. The carbon 3 has a methyl group and a chloro group, and not drawn, but we know it's there, is the hydrogen, and it has to be a wedge since the methyl is a dash. Carbon 2, again, it's leading out to a methyl, but not drawn, although we know it's there, is a dash and a wedge of a hydrogen. So think of all 4 bonds for each of these carbon positions. Examine carbon 2 first. Carbon 2 will be a dot, and what comes out of that? Notice coming down is a methyl group. I'm going to abbreviate the methyl as Me or CH3, same thing. Coming out in terms of the top are both hydrogens. So to the left and right, we have hydrogens. Notice the hydrogen that here would be a wedge is coming out to the right, and the dash is coming kind of behind the paint to the left. Now, in the second, let's consider, that was C2. Let's consider C3, and I'm only numbering them because I started here. I'm examining at carbon 2. So I use an open circle to represent carbon 3. What do we see? I see a chlorine coming up, so I'm going to represent that as Cl coming up. The methyl group is going to the left and behind the page, meaning that the hydrogen is going to the right out of the page. When we overlap those two pieces together, we get a Newman projection. Start with the front. Whoops. Carbon 2 had a hydrogen coming up and a methyl group going down, and we had a chlorine, methyl, hydrogen. So that's the skill that we're working as we draw a Newman projection. And keep in mind, these carbons are just free to rotate. I'll encourage you to think about holding carbon 2 fixed. So hold C2 in a fixed position and rotate carbon 3. When you rotate that in space, rotate it every 60 degrees. So rotate 60 degrees, chlorine will in the next spin, which is called a conformation. Every time I move the sigma bond, I'm creating a new conformer for that structure. When I rotate that 60 degrees, the chlorine disappears behind the hydrogen. Same thing here. When I rotate this again, the chlorine comes out, but now it's next to the methyl. And each time you're drawing this in a, kind of a loop, 60-degree turns, one gets hidden, then it comes back out. It gets hidden, comes back out. Rotate that and examine all the different conformations of this particular compound. So here's a sample homework question. It will say, draw the Newman projection, and it gives you the perspective of where to look. So here is carbon 1, 2, 3, 4. This will be a 4-carbon chain. I want you to stare down between carbon 2 and carbon 3. Make that your straight line. Carbon 2 is a dot on the page. I notice a methyl group coming up and to the right, and it has another methyl group coming to the left and straight down as well. So there are 1, 2, 3 methyl groups on carbon 2. Carbon 3 is an open circle. That's this guy, and what do we see? Well, coming up, I see a methyl group. Coming down in both directions are hydrogens. One will be a dash, one will be a wedge, but since they're the same, I'll just be able to place a hydrogen in each. That's the Newman projection for that particular model. What is that? 1, 2, 3, 4. So it's 2, 2 dimethylbutane. Now, build that molecule and spin it in space. Hold the front carbon still. And then spin the back carbon and watch what happens to all of the substituents. For example, when I spin the back molecule, the methyl group, spin it 60 degrees and draw the resulting conformation. Well, notice the red was in fixed position, so I'm just going to redraw the front carbon. I did not move it, I held it still. So that was just all in the fixed position. What I did spin was the green carbon in the back, and I did a spin by 60 degrees. So that placed the methyl group directly behind the red methyl group. The hydrogen now is coming out behind here, and this hydrogen is now hidden here. We'll notice that when groups have the most space between them, we have less steric hindrance. This is a more stable conformation. And when we stack one methyl group on top of another, we create large steric hindrance, and this is of higher energy. So when I say stable, it's of lower energy. And when I say less stable, it's of higher energy. And that just simply means we're getting interactions between these methyl groups because they're occupying the same space. We have electron interference, if you will. The like charges of the methyl groups as they interact with each other create repulsive forces, and that creates a higher energy system. And you know, in nature, things like to be at the lowest energy possible. That's the most stable conformation. Just how atoms would rather have a noble gas conformation because it's more stable, it's of lower energy. So as we twist and rotate, I am not saying that all of these conformers are created equal, but they do exist. As I twist those single bonds around between carbon 2 and carbon 3 in this example, every time I twist by 60 degrees, I'm creating another arrangement, another conformer, but they're not all of equal energy. The more space I have between these substituent groups, the lower energy, the more stable the conformation is. So you want to try another? Pause your video and try this out. What would this look like? Well, we're looking at a different angle. Let's see, I have 1, 2, 3, 4, 5, 6 carbons in the chain. At carbon 3 is a methyl group. So just practice nomenclature with me. This is 3-methylhexane. And we're going to look between carbon 3 and carbon 4. Alrighty. So with carbon 3, I'll make that the dot. Coming up and out of the page to the right would be that methyl group. Not drawn, but I know is there, is the hydrogen, right? That's this part. And I have a 2-carbon chain coming down, so I'm going to just abbreviate that as F for ethyl. You may certainly do a CH3, H, CH2, CH3. That's another perfectly acceptable way. Now let's decide what's happening at carbon 4. That's where I'm looking down between carbon 3 to 4 is the angle that I'm looking. What's on carbon 4? Well, let's make carbon 4 an open circle. From the open circle, I notice coming up is the ethyl group, a 2-carbon chain. And then not drawn, but we know is there, are the hydrogens. So I can place a hydrogen on either side here. When I overlap the two, place one on top of the other, I get the Newman projection. So this was carbon 3, and this represented carbon 4 in that 6-carbon chain. Put them on top of each other. I would have a methyl leading to a hydrogen, leading to an ethyl, and then in an open circle, the ethyl, the hydrogen, and the hydrogen. There's the Newman projection for 3-methylhexane looking from carbon 3 to carbon 4. Now again, if you hold the front carbon the same and begin to rotate the back carbon by 60 degrees, you begin to find all the different conformations. So for example, let me just hold the front carbon still. So I just redraw that as I see it on the page. But I rotate this group 60 degrees. So on the back carbon, the ethyl now gets hidden behind the methyl. The hydrogen is hidden behind that ethyl, and this hydrogen is stacked on that hydrogen. So we begin to see interactions. This is of high energy. It doesn't like to be stacked on top of each other. As a matter of fact, I can see what would be really nice about this is the ethyls, the largest functional groups, the substituent branch that is the largest, is 180 degrees apart from each other. That's a lot of room for them. This would be the most stable arrangement because it gives the most space to the largest functional groups hanging off there. When we think about analyzing all of these different conformations, I've highlighted what you're really trying to do is to make sure that the interactions between the substituents on the 2 carbons you're examining are given the most space possible. So that angle between atoms on adjacent carbons is called a dihedral or torsional angle. It's represented by 60 degrees in this picture. The front carbon is attached to a hydrogen. The rear carbon attached to a hydrogen. This bond angle is 60 degrees. So that's why I say when you're analyzing a conformation, spin the back every 60 degrees. Hold the front still and spin the back 60 degrees at a time. And you will see all the different possible arrangements for any particular molecule you're examining. The key is don't spin both, hold the front still. Now, absolutely, it's saying you could do it the same way. Hold the back still and spin the front. That's fine. You just need to hold one still and spin the other to see all the possible arrangements in space for the molecule, known as conformations. Now, of all those possibilities, there's really 2 that are most interesting that we'll examine. What is the lowest possible energy arrangement and what is the highest possible energy? Where do we have the most interactions and the greatest amount of crowding? And where do we have the least amount of interactions with the least amount of crowding? Those are the interesting energy conformations. And there's some vocabulary associated with conformation analysis. We'll talk about staggered conformation, and we'll talk about the eclipsed conformation. In this particular molecule, and think about what that is, it's simply ethane. It's 2-carbon chain, isn't it? Here's the first carbon, C1. Here's the second carbon, C2. So we have a methyl group, CH3, that's carbon 1. And over here is the second carbon and its 3 hydrogens that are attached. So a conformational analysis of ethane really is just asking us to rotate 60 degrees so that one hydrogen stacks on the next. If you rotate again 60 degrees, you've achieved the first picture. I mean, there's nothing unique. Rotate it once, they're stacked. Rotate it again, they're not. When I have the most room between those branches, it's known as a staggered conformation, that I do have indeed 60 degrees between those front hydrogen and the back hydrogen. When there's 0 degree bond angle between the hydrogens from the front and back carbons, it's known as an eclipsed conformation, and it is indeed the highest energy. That difference in energy between these conformations is due to hydrogen-hydrogen interactions called torsional strain. Really just two like atoms trying to occupy the same space creates higher energy due to the like charges of electrons repelling each other. So here's the difference in energy, and this particular HH interaction is about 12 kilojoules per mole. So what that means, kind of think of an energy diagram where potential energy is placed on the y-axis. So energy is increasing as we climb up the y-axis. And then notice what we're just representing are all the different conformations of ethane, all the different possible spatial arrangements of two carbons connected together, right? CH3, CH3. And this is the bond that I'm twisting between the two carbons. Carbon number 1 is attached to 3 hydrogens. Carbon number 2 is attached to 3 hydrogens. When the 2 hydrogens are given the space of 60 degrees, you're looking at the most stable conformation. And when I spin them 60 degrees and they have 0 degree bond angle, and remember I can't draw 0 degrees, I have to show you a hydrogen is there, and in your mind you're saying they're stacked on top of each other, that if I were looking at the red hydrogen, hidden directly behind it would be the black hydrogen. I don't see it, it's right behind it, a 0 degree separation. That's what's known as the eclipsed conformation. Every time I spin 60 degrees and go back between what we call staggered, spin again 60 degrees, we get eclipsed. Spin again 60 degrees, you're back to a staggered. These are all equivalent structures since we're only examining hydrogens. So the only type of interaction we're looking at is a hydrogen to hydrogen interaction. The difference in energy of the eclipsed to the staggered represents 12 kilojoules per mole, which is a significant amount of energy. So obviously things like to be at lowest energy possible. On this energy diagram, the staggered positions are favored. If it's possible to alleviate that 12 kJ per mole to a more stable conformation by twisting in space, it certainly will. So with that difference, I mean, it seems like such a small number, 12 kJs per mole, but it's really significant. Each time we have an H to H interaction, you're adding 4 kilojoules per mole of energy requirement to just stabilize the repulsive theory, those electrons that are at war with one another. So the total cost is 12 kJs per mole because each interaction requires 4 kJs. So at room temperature, 99% of these molecules are going to be in staggered conformation. That's the preferred conformation because it's of lower energy. This is a molecule a little more interesting. It's propane. So instead of just 2 carbons, we now have 3 carbons to consider. If we examine between carbon 1 and carbon 2 is going to have a methyl group on it. Or if I numbered the opposite way, one of the 2 carbons has a methyl. So instead of all hydrogens, I have a little something more interesting. I have a methyl group I can twist in space every 60 degrees. And we can analyze the torsional strain for propane as well. Notice carbon 1, if I just draw carbon 1, it's bonded to 3 hydrogens. So I can just represent that with 3 hydrogens. At the second carbon, I'll draw as an open circle, has a methyl group and 2 more hydrogens. So all I'm really doing is asking us to spin 60 degrees each time. So here the methyl group is pointing up. Spin it 60 degrees and you have what we call the eclipsed position. Stagger it again, 60 degrees, you're back to the original position. Again, these are all equivalent structures. There's just no other interactions other than a methyl and a hydrogen. So here the interaction is between methyl and hydrogen. Here the interaction is between hydrogen to hydrogen. Here the interaction again is H to H. Whereas the previous slide on our ethane, the only interactions, no matter where I looked, all the interactions were just H interactions. They were equivalent interactions. But with my propane, I have something unique only because I now introduce a methyl group. Here is a methyl hydrogen interaction, a methyl hydrogen interaction. And so it's just a little bit different energy than the two HH interactions. And that's why you see it a little bit higher instead of being 12 like the ethane was. Notice that this was 12 kJs per mole. The interaction for propane, is 14 kJs per mole, simply because the methyl to hydrogen interaction is even less stable. Because the methyl group is bigger, so it's going to need more room. And when I put those eclipse positions in there, it creates high strain in that molecule. Let's predict the energy barrier to rotation looking down any one of the carbon-to-carbon single bonds for the following molecules. So we're really looking at an energy analysis. We're going to draw a Newman projection and just compare staggered and eclipsed conformations. So let's take a look at the first molecule. I see the root word propane, so there's my 3 carbon. And on carbon 2, I have methyl groups. So there's 2,2-dimethylpropane. Let's examine a Newman projection staring down from carbon 1 to carbon 2. Let me make carbon 1 in blue. Carbon 1 is attached to 3 hydrogens. So I'll say carbon 1 will be a dot, and I'll just say looking up in all directions will be 3 hydrogens. All right, there's carbon 1. Let's switch to green for carbon 2. So carbon 2 is going to be represented with an open circle. And what do I see in all directions? Well, I see methyl groups. So I would have a methyl. Here's a methyl. And there's a methyl. Now I just drew the most stable conformation because I gave all the methyl groups 60 degrees to be away from the hydrogens, right? So that's the most stable conformation. But we're asking about interactions. So think about spinning this 60 degrees. The H moves to the methyl group. This H moves behind the methyl group. This H moves behind the methyl group. And you end up, now remember I left the front right where it was, and I only spin the back. And this time when I spin the back 60 degrees, every one of the methyl groups landed behind the hydrogen, right? So that's what the interactions are going to cost this molecule. We have an interaction of an HCH3. Remember that we assigned 4 kJs to each pair of eclipsing hydrogens and 6 kJs to eclipsing hydrogen with methyl. Well, each of these is an eclipsing hydrogen to methyl. They're all identical interactions. So what is the cost of energy to this molecule? Well, there's 6 kJs for each of these 3 interactions. So the total cost to this molecule to be in the eclipsed position would be 18 kJs per mole. From the staggered to the eclipsed position would cost 18 kilojoules of energy on our energy diagram. Let's try another. Let's examine 2-methylpropane. So instead of being di-substituted, we just have one methyl group on carbon 2. I'll make the front carbon blue here. I'm just going to say each carbon is leading to a hydrogen. So there's the first carbon. See how that's all leading to hydrogen, so any direction. Carbon 2 is leading to 2 methyl groups, and the fourth bond would be a hydrogen. So we'd have 1 hydrogen and 2 methyl groups. Now that looks like the most stable conformation because I've gotten those methyl groups as far apart from each other as I possibly can from those hydrogens. But let's spin this 60 degrees. And when we spin 60 degrees, we're going to stack those atoms on top of each other. So hold the front carbon still. And on the back carbon, let's spin all of those groups by 60 degrees. So this hydrogen, this is the behind carbon, and it spins 60 degrees. It's going to be eclipsed there. This methyl group will go here. This methyl group will go there. So we have coming off here now, we have a methyl. That's this guy. And then 2 more hydrogens. So here we have a methyl hydrogen interaction. And what did we say those cost? A methyl hydrogen was 6 kJs. And each hydrogen to hydrogen was 4 kJs. So here's 4 and here's 4 more for those bottom bonds. So we had 6 plus 4 is 14 kJs. So from the staggered conformation, to the eclipsed conformation, it will cost this molecule 14 kilojoules of energy. 6 for the methyl hydrogen interaction and 4 apiece for the 2 hydrogen-hydrogen interactions. As we build molecules a little bit longer, we've done ethane, a 2-carbon. We did propane, 3-carbon. We can begin to look at butane, the 4-carbon chain. So now all of a sudden, when we start examining a 4-carbon chain, between carbon 2 and carbon 3, each one of those carbons will have a methyl group that can interact with one another. So carbon 2 has 2 hydrogens and a methyl. Carbon 3, 2 hydrogens and a methyl, and how are all the possible conformations of spinning that single bond? So this is the one we're going to spin and see how all those interactions occur. So when I look at the Newman projection for a butane, the first carbon of butane, which would be C2 that you're examining, has a methyl group attached to 2 hydrogens. And the back carbon, which would be carbon 3, also has a methyl group attached to 2 hydrogens. There's the 4-carbon chain. Now, do you see what we did instinctively? We made the methyl groups as far apart as we possibly could to find the most stable conformation. Look here, it is of the lowest energy on our energy diagram when the methyl groups are 180 degrees away from each other because they have the most room to move around, right? They have their electron clouds, they have plenty of space. There's no torsional strain, there's no steric hindrance. That's the most stable conformation. But as I spin this now in 60 degrees, the methyl group, I can spin the front or the back because really these are the exact same carbons. If I spin in 60 degrees, you start to see methyl to hydrogen interactions or a hydrogen to hydrogen interaction. And so remember that even though I can't draw right behind each other, I have a methyl to hydrogen interaction here, a second methyl to hydrogen interaction, and a hydrogen to hydrogen interaction. Doing that math would give us 16 kJs per mole. What would be the most, let's say the least stable or the highest energy is stacking the two methyl groups on top of each other. What if I spun this methyl group all the way down to be behind the back methyl group? And that's what you're seeing here. Notice that's of highest energy. We have a methyl to methyl interaction and two hydrogens to hydrogen interactions. Whereas a methyl to hydrogen, and HH were the interactions here. These two are equivalent. This is of highest energy. Stacking those methyl groups creates the least stable conformation. Giving us the greatest bond angle between the methyl groups gives us the most stable conformation. And I can actually see in terms of unique positions, here is 1, 2, 3, and then looking at all the different ways to shape. And so this would be lowest. This would be kind of in the middle, although it's kind of up high, and this would be the highest. But since these positions are the same, these positions are the same, these two positions, they're the same. So I only have 3 unique conformations here. Those 3 unique conformations have specialized vocabulary that you need to know. Because there's 3 conformations, we need 3 words. I can't just say staggered and eclipsed like I could for ethane and propane, because there were only 2 unique positions for both of those molecules. Because they only had 2 unique conformers of high and low energy, we called them staggered and eclipsed. But now with butane, eclipsed, we have 3 unique conformations, so we need more words. Alrighty. So the first is called an anti. The anti is when the methyl groups are the farthest apart. And we said that this was the most stable conformation. The anti position on this potential energy diagram is when the methyl groups are the farthest apart from each other. All right, those are both anti positions. The term gauche. The methyl group experiences a gauche interaction when they are 60 degrees away from each other on carbon 2 to carbon 3 for butane. The front carbon has its methyl group 60 degrees away from the methyl group on the back carbon. That is called a gauche conformation. Back to this picture. The gauche conformation, do you see where they're 60 degrees apart? The gauche conformation shows where the methyl on the front carbon is exactly 60 degrees from the back carbon. The methyl on the front carbon is exactly 60 degrees on the back carbon. That is known as a gauche conformation. And it can be in the front to back or the back to front, is what we had pointed out. The highest energy of butane results when the methyl groups eclipse one another. And that's when they're actually just one right behind the other, right? That is the least stable, or you could say of highest energy. That costs the molecule about 11 kilojoules per mole for that torsional and steric strain. So the total cost, this highest peak right here, is the total cost of all those interactions. We know that H to H is a 4 kJ cost, and here's a second 4 kJ cost. But this guy here, this is an 11 kilojoule per mole cost, giving us a total of 19 kilojoules of energy between those conformations. And so when you look at the eclipsed position, you could have a methyl to methyl eclipsed, methyl to hydrogen eclipsed, or a hydrogen to hydrogen eclipsed. The gauche position is 60 degrees between the methyl groups on the front carbon to the back carbon. Highest energy is when the methyl to methyl is eclipsed. So we've analyzed all the possible conformations for butane. Let's practice some conformational analysis. Here's a molecule. Let's just count. This is 6 carbons long. So here I have on carbon 3 a methyl group of a 6 carbon chain. It says, let's rotate only the carbon 3 to 4 bond and identify the lowest and the highest energy conformation. So using our lessons from analyzing butane, knowing we really just want to give the most space to the largest substituent branches. Well, let's take a peek at carbon 3, and I'll make that the front carbon. And what do we see coming out? Coming up, I have a 2 carbon ring, or a 2 carbon chain. So coming straight up, I'm going to put ET for ethyl, a 2 carbon chain. So you could write CH2CH3, but I'm just going to write ET, it's fewer letters. What else do we see coming off of carbon 3? Coming out of the page, so coming to the right of my eyeball, because my eyeball is looking right up here from carbon 2 to carbon 3. This is my eyeball. So I see carbon 3 has a methyl group coming out and to the right, and it would have a hydrogen, not drawn, but we know is there, as the dash from that particular carbon. So when you see me write ME, you know that that is methyl. It's just easier to write and keep track as you spin things. There's carbon 3. Let's put carbon 4 behind it. And what do we see? Carbon 4 coming straight down is a 2 carbon chain. So I see an ethyl group. And then not drawn, but we know are there, are hydrogens. So I'll have the hydrogen coming out in these directions. Now, the way I drew it instinctively from the bond line, which is also the most stable conformation, notice that we have 180 degrees between the ethyl groups. That would be the lowest energy conformation. Right? The largest branches, those 2 carbon chains, are given the biggest space by not being near each other. If I wanted the highest interaction, let's keep the front, let's go back to blue. We'll keep the front carbon still, and I will spin the back carbon. And I'm going to spin it in a way so that the ethyl groups stack. So instead of coming straight down, the ethyl group is going to be directly behind the ET group of the front carbon. And when I turned it, those 2 hydrogens then they're also stacked. Alrighty. So what do we have for interactions? We have an ET, very high cost to a molecule. We have a methyl hydrogen interaction. And we have a hydrogen-hydrogen interaction. So those 3 interactions are of highest energy, specifically because the 2 ETs, the largest substituent branches, they're stacked on top of each other. We have a methyl hydrogen and a hydrogen-hydrogen interaction. So we've drawn the highest energy, and then the first one we drew was of lowest energy, giving the greatest bond angle to those ethyl groups. You have several of these. You want to try another with me? I'll do one. Hang out with me and do another. Identify the highest and lowest energy conformations. So I'm looking here at a 4-carbon chain, and on carbon 2 we have 2 methyl groups. Draw the highest and lowest energy. Well, let's examine carbon 2. We're going to be looking down the bond of carbon 2 to 3. Carbon 2, as I look straight down, is a methyl group. Looking up and to the right is a methyl group. And looking up and to the left is a methyl group. Carbon 2 is attached to 3 methyl groups. How about carbon 3? Let's make carbon 3 red. As I look up, I see a methyl. And then I don't see them, but I know they're there. The 3rd and 4th bond are hydrogens. So, is this the most stable conformation? Well, I have 60 degrees between the methyl groups in all directions. I don't think I can satisfy that if I start twisting, because notice these are all the same. They're all the same group. So as I twist 60 degrees, I keep creating the same structure for every second twist, right? Every 120, I've created the same molecule. So this is the lowest energy possible. And what would be the highest energy possible? Let's keep the front carbon the same. But now let's twist 60 degrees and show the back carbon now has a methyl group stacked right on top of a methyl. And of course the others will be hydrogens. And that should be an open circle there, not another dot, but that open circle leading from carbon 3. And now we have a methyl-methyl interaction, high energy, and we have 2 methyl hydrogen interactions. And so these interactions all cost the molecule energy. This would be the highest energy conformation. And notice again, even if I started spinning another 60 degrees, I'm just back to the same molecule I started with. If we look at this compound, again, just another homework practice. I'll do as many as I have in my paper. Hang with me if you'd like more practice. Here I have a 3-methyl hexane. And we're being asked to look between carbon 3 and carbon 4. That's different. I thought it sounded familiar. Carbon 3 has a methyl group coming up. So carbon 3 has a methyl and it has an ethyl. And not drawn, but we know is there, is a hydrogen. Carbon 4, I'll draw as an open circle, that's carbon 4, has an ethyl. So I'm going to just instinctively place it in the opposite direction there. So there's the ethyl group, and not drawn, but we know are there are 2 hydrogens, right? So get rid of that. So hydrogen, hydrogen. The reason I said let's draw that instinctively to give these guys the farthest bond angle possible. Those ethyl groups want to be 180 degrees away. That would be the lowest possible energy. Now this particular molecule has quite a few conformations. If I keep the front compound, the front carbon in the same position, but I spin the back carbon 60 degrees, right? So I'm going to spin this hydrogen now, comes up behind the methyl. This ethyl goes behind this hydrogen, and this hydrogen goes behind this ethyl. What do we have there? Well, we have ethyl to hydrogen interactions, 2 of them. And a hydrogen to methyl interaction. Do you see anything even of higher energy? What if we spin this again? Let's keep the front the same. That had a methyl, hydrogen, ethyl. But what if we spin again in the back? Spin this ethyl all the way over to where it's behind the other ethyl. Spin it again. And you'll find, coming off of the back carbon, an ethyl to ethyl interaction. Which is of highest energy. So this interaction where the two ethyls are stacked on top of each other, plus the hydrogen methyl interaction, plus the hydrogen to hydrogen interaction, creates the highest energy conformation. This is of higher energy than this, but we spin it to get the interactions of ethyl to ethyl, and that will dominate on that potential energy chart. So that was good work for conformations. We're going to come back to the next lesson and talk about cycloalkanes, things about stabilizing rings, and then really kind of ring strain and equatorial and axial bonds and all kinds of good stuff. So come on back for cycloalkanes in just a moment.